So now we're going to look at how we're going to do some word problems here called related rates. So a couple things to remember. dy dx means take the derivative of y with respect to x, right? So another way to think about it is if we're talking about rates here, which we are, we're going to come back to that idea that now a derivative, we're not going to be thinking slope of tangent line really in this section. Now we're going to be looking at the derivative as a rate of change. So if I look at dy over dx, this notation's a little better than y prime because it does kind of just itself, it sort of shows that we're talking about a rate of change, which we know is like change in y over change in x. It's like how much one quantity is changing divided by how much another quantity is changing. And we usually think of average rates of change because that's, that's how we do it when we subtract, y minus y over x minus x or whatever quantities we're trying to find the change in. That's really an average rate of change. But we know because of limits and then we get to the tangent line that we're really actually going to be talking about the instantaneous rate of change. And that's really the key here. Okay, it's not an average rate of change. When you do the derivative, you're finding the rate of change of a quantity at an instant. So for these problems, we're going to be doing them with respect to time. So it's always going to be over dt. So things like dA dt, that means the rate at which, say, an area is changing with respect to time. That makes sense, right? That over time, an area can change. So we're going to be looking at objects in motion. And this is where I start to say, like, calculus is the study of change. We've looked at finding the area of circles that aren't changing, that are static. Now we're going to start looking at some dynamic things where the circle is growing or shrinking. And we're going to find out at any given moment in time at what rate is the area of that circle changing. At what rate is the circumference of that circle changing. So that's what we're going to be looking at. So first, let's just look at some common formulas that we're going to have to use here in this section. And how to take the derivative and come up with your related rates equation. So let's look at this first equation. We're going to take the derivative of that with respect to time. So the derivative of A is dA over dt. Really, there's a 1 there, right? Because the derivative of A is 1. Then by chain rule, dA over dt equals, do the power rule, and we get 8 pi r times dr dt. Remember, 8 pi is just a constant. 4 pi is just a constant. So I'm doing power rule here. The 2 comes down, multiplies by the 4 pi. And so we get a new coefficient, reduce the power by 1, and then multiply by chain rule, dr dt. Now, this is why it's called related rates. Anytime you can put things in an equation, they're related. We've got one rate here and another rate here. Now you can think of these as their own variables, and they represent a quantity, a rate of change of a quantity. So we've got two rates in this equation, and they're related because they're in the equation. So that's why it's called related rates. So let's talk about what they mean. dA over dt, that means the rate at which surface area is changing. Okay, because that, well, let's just talk about what they mean. We'll get into that later. Got a lot to do here. So then dr dt, what does that stand for? That is the rate of change. I'll say it the same way. The rate at which the radius is changing. So in this original formula, r stands for the length of the radius. Here, r stands for the length of the radius. But dr dt stands for the rate at which the radius is changing. So you have to really know the distinction between these two things. What's the difference between r and dr dt? All right, let's look at the volume formula first here. If I take the derivative of v, I get 1, I'm not going to show that, times chain rule dv dt equals. Remember 4/3 pi here, this part, that's just a constant, right? It's just a number. So I'm doing power rule on r to the third. So the 3 comes down and multiplies by 4/3. And then I recopy the r, reduce the power by 1, and then I multiply by the derivative of the r with respect to time. So that's the chain rule again. What do the dv and the dr dt mean? Same thing here. dv dt represents the rate at which, put an arrow. I started using an arrow, so rate at which volume is changing. dr dt, that's a crappy r. dr dt is the rate at which the radius is changing again. It's called related rates because I've got two rates here and they're related to each other by this equation. So it's nice. I can take a static equation about volume and I can from that create an equation that relates the rates of change of those quantities. All right, now we're going to look at this guy. This might be, Pythagorean Theorem essentially, the length of a side of a triangle, whatever we want to talk about it. But the A, B's, and C's could be really any quantity, but typically we'll see that as like a distance or something like that. So let's take this derivative. So the derivative of A, well, there's a couple ways to do this. You can take the derivative of A to start and get 1 times dA dt. Now I have to do chain rule on this thing. So the 1/2 comes down. I recopy the inside. Reduce the power by 1 times the derivative of what's inside. So the derivative of c squared is 0. And then the derivative of b squared is negative 2b. And then I took the derivative of a b, so I got to chain rule it again. It's db dt. Okay, why is the derivative of c squared 0? Because c is a constant here. So now I'm going to simplify this thing. And I'm going to say that it is, let's see, the 1/2 and the 2, negative 2 can cancel. So we're getting negative b over the square root of c squared minus b squared times db dt. Now, if we don't really necessarily know what A and B represent in this, right, it could be some kind of picture where A is a length, it could kind of be anything. So we're just going to say that dA dt and dB dt, what do those represent? The rates at which A and B are changing, whatever A and B are. Oops. A and B are changing. Okay, let's look at the next one. Let's say we have a cylinder where the volume of the cylinder and R is a constant, right? So now R is not changing. Maybe we know the radius is staying like this. When this cylinder is changing, maybe the base is staying the same, but it's just growing in height. So H is the only variable here. R is a constant, so we can treat R as such. So that means that pi r squared is just a constant, a number. So I'm just doing power rule on this thing. So the derivative of V is 1 times dV dt for chain rule. And then it's the derivative of H is pi r squared H is just pi r squared. Because it was like if this is a number, let's say this number is 6, right? The derivative of 6H is just the 6. We do power rule on the H. Times, though, we did take the derivative of an H. Even though the H is no longer in the equation, we did take the derivative of an H, so it's times dH dt. Okay, so if this is a volume of a cylinder, we know what these letters represent. So we're going to say dV dt is the rate at which the volume is changing dH dt is the rate at which the volume, at which the height is changing. And my pen just died here, so I'm going to charge that, and I'm going to pause. So it's dH dt is the rate at which the height is changing. Here's one of your trig ratios. This triangle may be growing, the angle could be growing, the sides, who knows. Some things are changing, some things aren't. In this case, it's pretty clear that theta and x are changing, but 15 is staying the same. You know, this could be an airplane flying overhead. It could be, who knows, a ladder falling down a wall. That's a classic one. So we'll have to take the derivative of this guy. So the derivative cosine is negative sine theta. And since the variable was theta times the derivative of theta with respect to time equals, now if you think of the derivative of x over 15, over 15, that's just a constant that comes along for the ride, right? So you could think of it as 1/15 times x. And if you take the derivative of that, you get 1/15. You did, however, take the derivative of an x, so it's going to be times dx dt. This is, and so this is where d theta dt represents the rate at which the angle theta and side x are changing. I just want to write them out all the time. I already said d theta dt and dx dt represents, you get the point here, right? This is what we're trying to go for. So I'm trying to break, you guys have it down. You have it down that derivative means slope of the tangent line. I think way back when I introduced that, I said it's very important you have to know that, but that's not the only way that we think of a derivative. I think I mentioned that, right? A derivative is also a rate of change, especially in these application problems. So now I'm going to, try to kind of drive that home. That's what all these derivatives mean. It's always the rate at which this quantity is changing. And keep in mind, it's always different than theta itself. Theta might be pi over 3. That's just the measure of that angle. But d theta dt is going to be the rate at which it's changing, and it's always going to be in radians, by the way. All right, volume of a cone, last one. Let's see if you can do this one. Pause the video, and then we'll see what I got. All right, so this is what you should get here. It was product rule. We didn't say any of these are constants. So now I think of this as my first function times that as my second function. Inside of here, the 1/3 in the pi, that's my constant. So I can do power rule on that. So the 2 comes down and multiplies by that, hence the 2/3 pi. Then I reduce the power of r by 1, so there's the r, and I took the derivative of an r, so it's dr dt, times, recopy the second function, h. And then I just reverse that, recopy the first function times the derivative of h. Now all of these rates represent the rate at which those quantities are changing. So this time I didn't want to write it 3 times. So it represents the rate at which volume, radius, and height are changing.